Thank you, everybody, for joining us here in person and online. We have PhD student Michelle Spencer joining us today for the boundary layer seminar, and she'll be talking to us a little bit more about the tracer experiment and the work that she's been doing on that. Michelle works with myself and Dr. Petra Klein with the observation data sets that we collected down in Houston for that data set, and she is working toward the final part of her dissertation work. So we're excited to see how she's moved forward with the data.
Good. Thank you, Liz, for that introduction, and thank you everybody for coming and joining in my seminar, both everybody in person, but all of you online as well. So getting into it, the planetary boundary layer, or the PBL, is the dynamic interface between the Earth's surface and the atmosphere. This portion of the atmosphere is pivotal in driving meteorological processes that influence weather patterns, climate behavior, and pollutant dispersion. The PBL responds to surface forcings on the order of minutes to hours and exhibits a distinct diurnal cycle, an example of which you can see in the figure here on the right-hand side. This particular figure helps to depict the numerous features and pieces that make up the PBL, with the growing convective mixed layer shortly after sunrise, the residual layer after sunset, and the nocturnal inversion that makes up the stable surface layer in the overnight period. Given that the PBL is directly influenced by Earth's surface, the characteristics of the PBL vary from location to location because of the spatial heterogeneity of the Earth's surface. One of the key parameters that are associated with boundary layer research is the PBL height, which is important to many forecasting and modeling applications, such as those for air quality, convection initiation, and modeling parameterization development. While this is an important parameter, it's difficult to define and hard to observe, partially due to limited observations throughout the depth of the PBL. The heterogeneous nature of the PBL, temporally but also spatially, also adds to the difficulty of estimating these PBL heights. As such, we rely on observations of different PBL characteristics with things like thermodynamic profiles, vertical velocity observations, and aerosol concentration measurements to estimate the PBL height. Several different instruments and methods are used for this, with a large portion of past PBL height-related research relying on radiosonde observations for estimations, but there has recently been a growing number of studies that have begun utilizing space and ground-based profiling systems like ceilometers and lidars. These different instruments use a variety of methods for determining the PBL height, whether that be the location of temperature or humidity gradients, or the height of aerosol gradients. An example of some different radiosonde-based PBL height detection methods is shown here in the figure on the right, provided by Ariana. Thank you. The left-hand panel shows a clear sky case, while the right-hand panel is a more complex non-clear sky case. On the simpler case, there's considerably less variability in the detected PBL height estimations between the different methods. But when you look at the more complex case, the various methods result in differing estimations of where the PBL height is, and some of them being as great as 1.5 kilometers different, which can have significant impacts on forecasting applications. For this particular project, we use a fuzzy logic method that combines multiple observation sources that I'll explain furthermore in a moment. But for now, we've established that the boundary layer can be a complicated place to understand because of both limited observations, but also a large amount of variability because of the nature of the land surface. So why not add a little more complexity to the mix, right? Coastal urban environments in particular experience unique and complex PBL processes and interactions due to the combination of influences from mesoscale coastal breeze circulations and urban heat island effects, which you can see an idealized example of which here on the left-hand side. This particular figure shows an example of the progression of land and sea breezes and city pollution. In the early morning and early PM hours, you have the land breeze that's advecting the pollution out over the sea. But as you get into the early afternoon hours, a sea breeze can develop, acting to advect that pollution back over the city. Not only this, you have areas of enhanced convergence along that sea breeze front, which can act as a lifting mechanism and trigger convection. In addition to these coastal breezes, the land atmosphere interactions are affected by the heterogeneous nature of the land cover from the land to sea and the surface roughness changes that are associated across this region. These different land characteristics and processes lead to unique dynamics that can significantly influence local weather, particularly air quality conditions. Coastal urban regions often experience unhealthy air quality levels, especially in port locations where you have an increased amount of pollutants from shipping and freight operations. An example of the ozone exceedance days for the Houston area is shown here on the bottom right figure for a 23-year period. While there has been a gradual decline in the number of 8-hour ozone exceedance days, there's still over a month's worth of days reaching unhealthy levels. Given that a large portion of the world's population lives within these coastal urban regions, it makes this area a really important place for us to continue studying and further our understanding of some of these smaller scale processes. Understanding the behavior of the atmosphere and how it interacts with the land surface can be important for a multitude of applications, especially within these particular environments, including things like water resource management, air quality forecasting, and sustainable urban development practices, thus leading to the work that I will be sharing with you here today. So Houston, which is the 4th largest city by population in the United States, is a prime coastal urban environment for us to study, with it being home to a complex aerosol makeup, frequent summertime convection, and compounding small-scale meteorological processes. The city has a history of poor air quality, as we saw on the last slide, in part due to the numerous pollutant sources from this urban region, including things like oil refineries, transportation, shipping emissions, and agricultural operations. Many operational numerical models also struggle to accurately simulate the PBL in Houston and its summertime convection and small-scale processes that take place in this area, which really necessitates more research into these complex issues, which brings us to the Coastal Urban Boundary Layer Interactions with Convection campaign that took place in the Houston Galveston region from June 1st to September 25th of 2022. The project really aims to investigate and understand the many complicated mesoscale circulations, processes, and interactions that take place throughout this region and how these processes modify our planetary boundary layer. So for this campaign, we deployed 3 different mobile profiling units in a semi-linear transect through Houston, which you can see here in the map on the left-hand side. Each site was chosen specifically to sample different PBL environments, with Clamps 1 acting as our urban location, Spark as our rural location, and Clamps 2 as our coastal site. This map and the shading that you see within this map represents the local climate zones for the region, and while Clamps 1 and Spark are sited within similar zones, the air masses are expected to be different, with Clamps 1 being downwind of the greater metropolitan area of Houston throughout the majority of the campaign. So each mobile profiling system collected continuous thermodynamic and kinematic observations throughout the depth of the PBL, with only minor data gaps due to instrument issues or brief significant weather events. An example of some of the data that we collected throughout Cubic is seen here in the top right figure. This particular day included a sea breeze passage over our clamps 1 location, which led to increased moisture within the PBL and decreased vertical velocity observations. The bottom photo here is our clamps 2 location. This was at the University of Houston coastal site, and really just wanted to include this so you get an idea of what the instrument profiling systems kind of look like here. So, as I mentioned earlier, I've applied a fuzzy logic algorithm that uses the kinematic and thermodynamic profiling data that we collected to estimate our planetary boundary layer heights. Fuzzy logic algorithms and methods have been used within the atmospheric science community for many years and recently have been applied to PBL height estimations. The algorithm that we use here uses a combination of membership functions and Haar wavelet transforms in a 2-step approach to come up with a final estimated height. The first step involves the use of measurements of mixing, such as vertical velocity variance or the height of temperature inversions, to determine the first generation aggregate. Then a check is applied to ensure that this first generation aggregate is connected to the surface by using a threshold of 0.5. So we find the height at which that threshold gets below 0.5, and that is marked. The second generation and second step is using indicators that mixing has occurred. So things like the signal to noise ratio or constant wind speeds within a layer depth. The same aggregate threshold and check is used on this second generation estimate, and then the estimated heights are smoothed via triangle mean to result in the finalized height estimations and uncertainties. This particular algorithm was created by Dr. Smith and Carlin and expands on the work of Bonin et al. 2018, in which they only use lidar measurements with the fuzzy logic method of detection. The addition of the thermodynamic data can help the accuracy of the algorithm during transition periods when temperature inversions have a greater impact on the PBL height. These thermodynamic data and the methods that are used help to ensure that the PBL height is connected to the surface, which is a key distinction between the PBL and the mixed layer depth. The code is openly available, and you can find it on OAR's Atmospheric Observations GitHub page. The URL is listed here. And to give you an example of what these heights look like for each of the first and second steps, the figure here on the left-hand side shows that. We have our first and second generations, as well as breaking down those estimated heights into the mechanical versus buoyant terms. If you are interested in knowing more of the nitty-gritty details of how this works, this algorithm flowchart is also available at the GitHub page, so you can see how exactly this is working. So once the PBL height algorithm was applied to each site for the duration of the campaign, we can really get into the analysis and start getting an idea of the PBL characteristics throughout the Houston area. Here we have the campaign averaged PBL heights for each of the 3 sites. Focusing in specifically on the daytime boundary layer, we can see that the timing of the maximum PBL height and the differences in depth of the PBL are pretty significant between the 3 different sites. Clamps 2, which as a reminder was our coastal location, reaches a maximum PBL height of approximately 1,100 meters just before 18 UTC or 1 p.m. local time. Clamps 1, which was our urban location, however, doesn't reach its maximum height of about 1,500 meters until a little over an hour and a half later in the day. Additionally, the maximum depth of the PBL ranges about 440 meters between Clamps 1 and Clamps 2, despite there only being a distance of about 60 kilometers between those locations. Now, looking at these averaged heights can give us some insight into the general spatial and temporal differences, but just how variable can these heights be? To look into the variability, I have here the maximum and minimum heights for each time at each site, which really kind of just gives us a visual of how the spread is throughout the campaign with these boundary layer heights. Much like the average heights that we saw on the previous slide, the PBL at clamps 1 is consistently deeper compared to sparks in clamps 2, possibly indicating more vigorous mixing at this location. With clamps 1 being located within an urban setting, the environment is likely being influenced by the urban heat island, which could also explain the generally deeper PBL depth that we see in this overnight period. This also helps us shed light on how variable the clamps 2 and spark heights could be, where the maximum height could be reached anytime within a span of several hours, rather than the kind of more singular peak timing of PBL height seen at clamps 1. This difference in peak timing is likely being influenced by the sea breeze, which often influences clamps 2 and spark, but doesn't always reach the clamps 1 location, or reaches it so late in the afternoon that we've already entered into that evening transition near sunset time. So naturally, this leads to kind of our next question of what factors are actually contributing to these spatial and temporal differences that we're seeing. To begin investigating the different aspects that may be responsible for the variability in the PBL heights, we use self-organizing maps to categorize our synoptic regimes over the Houston area. This is a machine learning technique in which data is provided and a pre-described number of nodes are given to the algorithm. And this algorithm then finds patterns within the data and produces results like what you see here on the left-hand side. For our specific SOMs, we use a two-step sorting approach where we use 21 years worth of summertime geopotential height data from the AERI 5 archive. We chose the 700 hectopascal heights for this so that we could capture the near-surface synoptic flow patterns, but have minimal effects from the Sierra Madres Mountains to the southwest of our domain. We applied a two-stage sorting to this, with the first one using an 8x8 set of nodes, which resulted in a node containing only tropical cyclone cases. So we removed those tropical cyclone cases from the data set since we're not really concerned. That's kind of outside of the scope of things we're considering in this study. We verify those against satellite imagery to ensure that that is actually what they are, the type of cases they are. And then we do an additional sorting step and produce this 3x3 set of nodes in which we have distinct different synoptic patterns over the Houston area. The table here on the bottom right is just some quick statistics regarding these synoptic flow regimes. Over the full 21-year period, Houston experienced southerly winds about 69% of the time. And this is really similar to what we saw for the cubic specific dates in which we had southerly winds 70% of the time. The second most common regime that Houston experiences is a northwesterly wind flow over the city, which occurred on 21% of the days throughout cubic. So looking at how the PBL height varies across these synoptic regimes, we can see that the heights show little variability from site to site for the different regimes. While there are some indications of deeper PBL depths with the northeasterly regime at clamps 2 and spark, this only included a couple of cases, so we have to take that with a grain of salt. Our results here indicate that the synoptic regime does not account for the PBL height variability that we saw throughout the campaign, which means that local and smaller scale processes are driving the differences in these heights. So obviously, with Houston being a coastal location, the sea breeze is affecting our planetary boundary layer, and it's known to modify that PBL. But just how much it modifies different characteristics is not really well understood, especially when looking at it in a spatial sense. So focusing in on the sea breeze and how it may be impacting the PBL, I have here two different cases from clamps 1. On the left-hand side is a case in which there was not a sea breeze that was observed at this site. And we can see kind of your typical PBL evolution throughout the day with the growing convective mix layer, taking shape just before 14 UTC, a gradual building of this mixed layer before reaching a pretty steady height of about 1,600 meters for a few hours before starting to decay around that evening transition time. On the right-hand side, we have a sea breeze case, and not only do we see differences in this PBL height evolution, but we can also see some differences in the characteristics and parameters within the PBL itself. So if we zoom in a little closer to this sea breeze passage, we can see that there is a clear decrease in the PBL height as the cooler and more moist air mass advects over the clamps 1 site. There's also a decrease in the magnitude of our vertical velocity observations, indicating less turbulent conditions after the sea breeze front passes over. Now, this is just a single case and a single example of how the sea breeze can affect the PBL, but just how different are the PBL heights when we compare sea breeze versus non-sea breeze cases throughout the campaign. So that's what we have here with our campaign averaged heights for the 2 types of cases. The sea breeze cases are the solid lines, while the non-sea breeze cases are our dashed lines. The sea breeze results in deeper PBL heights at each of the 3 sites, with the greatest differences occurring at our coastal and urban locations. Interestingly, though, the time that the maximum PBL height is reached does not vary much between these averaged 2 different types of cases. So not only do we not see much in the timing of the peak PBL heights, when you compare sea breeze versus non-sea breeze cases, the rate of decay in those PBL heights is greater on our sea breeze cases. The next question is whether we can quantify the amount of influence different PBL characteristics have on these PBL heights. Now, I haven't gotten much into answering this yet, but I'll share with you some of the very initial stages of trying to do so. For these last couple of slides, I will be showing time series plots where our x-axis and our time axis is normalized by the time at which the maximum PBL height occurs. This is by no means a perfect method because it's not taking into account other processes that can affect the timing of when your maximum PBL is reached. But for now, this is what I've got. So we will look at it here. So this is a 6-hour time series, 3 hours before and 3 hours after our maximum PBL heights. This one specifically for our vertical velocity variance averaged over a deeper layer from 50 to 500 meters. Here, we can see some slight influence or slight changes between the sea breeze versus non-sea breeze cases with a little bit of enhanced and elevated turbulence on the sea breeze cases, particularly at clamps 2, compared to the non-sea breeze cases. If we look at our low-level temperatures, we see a greater difference in the low-level temperature signatures with warmer temperatures on sea breeze days compared to non-sea breeze days. We also see that we have this steady increase in temperatures before the maximum PBL height is reached, which you'd kind of expect, but we don't see much of a decline of these temperatures immediately after that PBL height is reached. So there is a greater spread as well. If you compare our vertical velocity variance, there's not as much of a spatial difference between these variance calculations or variance results. But when you look at the temperature, you can see that spatial difference quite a bit. Especially between our rural and coastal locations. So that's what I have so far for today. Some of the biggest key takeaways thus far are that the PBL height varies spatially and temporally throughout the Houston region. We found that the synoptic conditions don't account for this PBL height variability, leading us to look into smaller and more local scale type of processes to explain the PBL height variability, and that sea breeze cases do result in deeper PBL heights with quicker PBL height decay. Some of the next steps to further this research are to nail down a method for quantifying the influence of different PBL height or PBL parameters on the resulting PBL heights. This is not a straightforward thing to do, given how different the timing can be for like sea breeze arrivals at these different sites. So open to suggestions there. Also, with this being a coastal urban location, being able to quantify the urban influences on these heights and other PBL characteristics is important. Haven't gotten there yet, but I want to. So with that, a big thank you to everybody for coming today, and to my husband, advisors, colleagues, friends, family, and my cat, Iro, for all of their help and support. And with that, I will take any questions.
So we could open the room and online for questions.
So, sorry, my voice is giving out. What motivated the layer heights to choose last couple slides? Because I noticed they were different between velocity variance and the thermodynamic. And also, when you did your variance, was it doing the time series variance and then averaging that height, or did you do the variance like the whole?
Okay. So what motivated the different layer heights? I did not have a motivation. I played around with a bunch of different height levels, and the same general trend was seen, and it didn't matter. So that is something I'm still trying to figure out the best method for which layers to look at there. And the way that the variance is calculated, sorry, can you ask what did you?
So there's two ways you can do it. You can take
Yeah.
the time height variance, or you can take the time series variance at each level and then average that.
So I averaged over the height first and then time.
Okay, so you average for velocity.
Yes. Yeah. Ariana?
Do you think there would be any value to looking into other PBL methods or these results or others?
I think that there could be value because there are limitations, like this particular algorithm that we used. If you have, you can be limited by your aerosols in the depth at which your lidar can see. So I think that there could be value. However, we don't have continuous observations in a different way. So we could compare against radiosonde observations for those specific times. But one of the big takeaways from this particular data set is having that continuous time series of the heights. So I think there's value in different ways, but trade-offs. Petra?
If I remember correctly, we saw that for the sea breeze days, the boundary layer was deeper before and after the sea breeze passage. Not correct. When you, yeah.
So
this would indicate that the sea breeze, on the sea breeze days, the boundary layer will remain steeper even after the sea breeze passage, correct?
yeah, so it's interesting because we showed like the example case where you have this immediate decrease in the PBL height. That's not always what happens with the sea breeze passage. So this particularly is looking at an average sense, but because our sea breeze happens at different times, you kind of have to keep that in the back of your mind when you're comparing this specifically, because even at like clamps 1 or clamps 2, the sea breeze can happen early or late, and there's a span of up to 6 hours at one specific site. So you kind of you miss out on the immediate sea breeze since this isn't normalized by the sea breeze time. but
I just find it interesting even to see that pronounced difference before the sequence passed. To some extent, not what I expected to see. That we see. I mean, maybe the reason for it is that the sequence happens on days that we have a lot of thermally driven flow, a lot of thermally driven heating of the boundary layer.
yeah,
Which would indicate that it can expect a deeper boundary layer, but it's not what I initially expected to see.
it wasn't what I expected to see either. I expected the opposite of what I've seen, which is part of why I wanted to get into the different specific PBL parameters to try to tease out, you know, are we having greater vertical velocity magnitudes? Are we having much higher temperatures that are related to it? So still teasing out the reason why we have this, but
So the algorithm gets one estimate of the PBL height. So if you had two features, like let's say like an upper level PBL height, and a sea breeze comes, will your algorithm get one or the other? Does that work?
So that's a really good question. The way the algorithm works, by using the aggregate threshold that we have, we're still ensuring that we're connected to the surface. So if you have the sea breeze come through and it's not, we don't see a distinct big enough gradient or difference, it's not going to capture that height specifically. I'm not sure if that necessarily answers your question or not.
So it could detect, say, the sea breeze, but not different types of or down like the old PBL. So what I'm wondering about, like, so you have a high PBL, say, for the sea breeze.
Mhm.
And the sea breeze comes through, that'll be the altitude. What happens to the PBL height that formerly was in the last PBL height that elevators identified?
So
Possibly,
I think it's actually more of the opposite, because the PBL, the change with the sea breeze isn't super large most of the time. We're actually keeping that higher layer, because if we look at cases like this one specifically, you can kind of see where you would expect the sea breeze to be based off of like our vertical velocity difference right after it passes, but we're still capturing and identifying our PBL height as being that upper level, if that makes sense. So
on the left panels, but let's draw off that line. So that PBL height that's being drawn.
yeah, so this line is our PBL height that the algorithm has estimated.
And so post sea breeze front, is that line corresponding sea breeze boundary?
So the sea breeze initially passes over at this line that I've detected here, or that I've put in here. And our heights, the algorithm is still detecting our heights as being this black line. So we're having a difference in modification to the lower level, you know, PBL characteristics, but it doesn't track the height of the sea breeze front specifically. Like,
It's not a sea breeze front. Because the
like,
where the solid line has to be,
mhm.
looks like it's traced to the outline with data. See, at least a little bit. But then, like after the sea breeze passage, that sort of data cutoff goes to white. That's still there.
Yes.
It's not, I don't know what it should be. It looks like something's going on.
So the algorithm is a fuzzy logic algorithm, and so it's working in terms of aggregate, right? And so it'll take time for the atmosphere to respond in enough of a way for the aggregate to respond to the sea breeze effects, right? So what we're seeing is a gentle decline in the boundary layer height is detected by instead of a step change.
Does the algorithm tell you which members must be brought in? Trigger the votes?
Well, so it's a aggregate sum from all of them, right? And then the boundary layer height is detected where the aggregate sum crosses a threshold value. So no, you could go back into the code and write all of that out if you wanted to. But it's intentionally not, doing step changes. And so above that, if you look at the aggregate fields, if you go back to your example of the code, if you look at the actual aggregate fields, you'll see that the aggregate does have signal, like the one, I think one more maybe. You show the aggregate?
No, I just have the examples of
Okay.
different.
You
Yeah.
do actually output the aggregate itself, and so we think plots like this where you actually see, the sums of the aggregate.
Okay.
And so you can see that there are returns, like for the residual layer, basically, because there are areas where the aggregate drops below the basically membership threshold. It's not counted as surface boundary layer. So you can also rewrite your threshold values and also let the text residual layer or whatever we would call that. Yeah. So that information is there.
Okay.
I guess in the example that we were looking at, what is interesting is that there's still so much missing in the boundary layer. Kind of run through that when you're mixing. So it would be interesting to see why was the boundary layer high?
Yeah, so I think what's happening here is look at the time of day.
Yeah.
Yeah.
And so your weighting is changing as well because different features are becoming more significant to boundary layer foresights, right? And so in the algorithm, weighting is now changing for some of those inputs.
So it's probably the thermodynamics that have a higher
Yeah.
weighting.
Yeah.
Yeah, so the thermodynamics are now starting to gain weight in the algorithm because the sun is setting.
And I mean, if you look at the vertical velocities, I mean, it is starting to trace in between this kind of separated
Yeah.
plumes, right? Like we have these plumes that are above this kind of surface layer of plumes. So.
Yeah.
Maddie?
I have a quick question on some of your more recent things that you showed with your vertical velocity gradients. Good. I found it interesting. It's like you see at least I see amps to sparks like the cyanotic lines.
Mhm.
It feels like that's pretty much straight across. Whereas there's one. I think it's black, right?
Yes.
How that is off after maximum PBLH. Do you think that could be due to urban de-idling effect or anything else to just about that?
I think that this decline at clamps 1 that we see is more associated with the early evening transition because the timing of the maximum heights at clamps 1 occur later in the day in general. The spark calculations that I did that you see in the vertical velocity variance are suspect. So I don't know if I messed something up specifically with that or what, but the later maximum PBL heights that occur closer to sunset, I think is what explains that difference between the after max PBL signature that we have here.
I think we can thank our speaker.